In the previous online session, we just discussed the exponential distribution. We use exponential distribution to model the randomness of inner arrival time for customers. We can also, in this online session, we are going to look at a different distribution. It is called a Poisson distribution. So we use Poisson distribution to look at the number of customer arrivals in a period, for example, per hour, per minute, per day. As we said in the very first example, the arrival rate was 10 customers per hour. When we say the arrival rate was 10 customers per hour, it measures the average process. It does not mean every hour you will see exactly 10 customers. It can vary. It can be 5, can be 10, can be 20. So now we have to look at a distribution called Poisson distribution to model such randomness. So basically, one information we know is if the inner arrival time follows exponential distribution, then the number of customer arrivals per period will follow Poisson distribution. So these two distributions actually model the same process, but from different perspectives. In the next few slides, we'll show you how these two distributions are correlated. The whole process is called a Poisson process. So if the arrival rate is lambda, it can be per hour, per minute, per day, then we can calculate the following probabilities. The probability that there are exactly n customer arrival in a period of time t is equal to, this is a little bit complicated formula. So first of all, we have a power function. So here, n is the number of customers, n customers, n is how many. Then we have an exponential function. Then underneath, we have n factorial. So some of you may not remember what is factorial. So factorial is defined like this. 0 factorial equal to 1, 1 factorial equal to 2, 2 factorial equal to 1 times 2, then n factorial is 1 times 2 times all the way to n. So this is how we define factorial. So basically, we use Poisson distribution to capture the randomness in terms of how many customer arrivals in a single period. So this is a function, this formula to use to calculate the probability. So in order to apply the formula, we need to know several pieces of information. First of all, we need to know the arrival rate, lambda. We also need to know the length of the time period, which is t. Then we need to know n. N is the number of customers. So both n and t, you can look for the information about n and t in the problem. So lambda is just arrival rate. Let's look at a sample example. Example 3. The average inner arrival time is 2.4 minutes. If a patient has just arrived, how likely there will be no customer arrival in a period of 5 minutes? So read the question again. The average inner arrival time is 2.4 minutes. If a patient has just arrived, how likely? It's about likelihood there will be no customer arrival in a period of 5 minutes. So first of all, what is 2.4 minutes? So 2.4 minutes is the average inner arrival time. So basically it means 2.4 is A. So A is equal to 2.4 minutes. If a patient has just arrived, how likely there will be no customer arrival in a period of 5 minutes? So a period of 5 minutes, that means the time interval we're talking about here is 5 minutes. So this is T. So by reading the problem, we know that A is equal to 2.4, but A is not sufficient. In order to apply the formula in the previous slide, we know we need to find out 3 pieces of information. What is T, what is lambda, and what is N? So we don't really need A, but we know A and lambda are interchangeable. So knowing the value for A is equal to 2.4 minutes, we can convert the value for A to the value for lambda. So lambda is equal to 1 over A, so the 1 over 2.4. So we're getting 0.4167 per minute. So this is the lambda. In other words, on average, we'll see 0.4167 patients per minute. We want to find out the likelihood that there will be no customer arrival in a period of 5 minutes. In other words, how likely you will see 0 customer in 5 minutes. So 0 customer, the number of customers 0 in a period of time of 5 minutes. So it looks like this is the time to use to apply Poisson distribution. So we can use a formula. This is a formula to calculate the probability. So how likely you will see 0 customer in 5 minutes. So here, n number customer equal to 0. We also know the value for lambda. We also know the value for t. T is 5 minutes. So we're plugging all these values. We can do the calculation. So here, the calculation involves 3 terms. The first term, this is a power function. Lambda, which is 0.4167, t, which is 5 minutes. The second term is an exponential function. So it's negative 0.4167, so it's negative lambda times 5, which is time. Then we have factorial 0. So this is equal to 1. You do the calculation, you'll get 0.1245. In other words, how likely? It's about 12.45% time you will see 0 customer in a period of 5 minutes. So one thing I want to point out about how to apply this formula is make sure you always use the same time unit for lambda and t. So in this case, because lambda is at 0.4167 per minute, so it's a per minute arrival rate. Because it's a per minute arrival rate, when we use that value for t, we should use t in terms of how many minutes. So per minute versus minutes, they are consistent. Some other times, you may see lambda is per hour rate. If lambda is per hour rate, you want to use time in hours. So per hour, hours are consistent. Per minute and minutes are consistent. So they have to be consistent. Now let's look at another example. The average arrival rate at a bus station is 15 minutes per hour. The average arrival rate is 15 minutes per hour. What is the likelihood that there will be exactly 2 customer arrivals in the next 10 minutes? 2 customer arrivals in the next 10 minutes. So first of all, what is 15 customers per hour? 15 customers per hour, obviously, this is lambda, arrival rate. So what is that next 10 minutes? Next 10 minutes, that's a time interval. This is t, next 10 minutes. So by reading the problem, we know that lambda is 15 per hour, or we can also convert it to 0.25 per minute. So by dividing by 60, so you get 0.25 per minute. So again, we have 2 different values for lambda. So lambda equal to 15 per hour. Lambda is also equal to 0.25 per minute. They are equivalent. So we want to find out the probability that there are exactly 2 passenger arrivals in the next 10 minutes. So 2 means n is equal to 2. So 2 customers in 10 minutes. N is equal to 2. T is equal to 10. So by applying the formula presented on PowerPoint slide 8, we can just plug in all these numbers. We do the math. It's a little bit messy. It can take a little while. Then you'll get a probability 0.2565. In other words, a little bit over 25% chance you will see exactly 2 customer arrivals in the next 10 minutes. So here, be careful. When we apply the formula, in terms of lambda, we have 2 lambda values. One is lambda is equal to 15 per hour. The other one is equal to 0.25 per minute. The question is which number to use. Shall we use 15 or shall we use 0.25? Again, for consistency reasons, because the t is 10 minutes, we better use 0.25 per minute, okay, for consistency reasons. So here we use lambda equal to 0.25 per minute, not 15 per hour. It's because we want to have consistent time units. So far we covered two kinds of distributions. So one is called a Poisson distribution. The other one is called exponential distribution. Actually, they are related. So both Poisson distribution and exponential distribution, they capture, they model the same process. It's called Poisson process. So if a process is a Poisson process, then the number of customer arrival in a period follows Poisson distribution. The inner arrival time between two consecutive customers follows exponential distribution. So these two distributions are different, but they model the same process, which is called Poisson process. So Poisson process has a lot of applications in service industry. For example, call centers, ER rooms, where customers are making individual independent decisions about when to arrive. So this is called Poisson process. If you look at this graph, it gives you a better idea. So what's the relationship between a Poisson process, Poisson distribution, and exponential distribution? So both distributions are used to model the same process, which is Poisson process. But however, we're looking at a different perspective. For example, this line shows the time and also shows arrival time for different customers. So if you start at time 0 and keep counting how many customer arrivals in each hour, so from 0 to, for example, from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, you keep looking at the number of customer arrivals in each hour, then you will see the first hour I have 1 customer, the second hour I have 2 customers, the next hour 0, the next hour you have 4 customers. So if you're looking at the number of customers per hour, like the top view, basically you can use a Poisson distribution to model such process. It's a one perspective. A second perspective, you can look at the process, it's called a bottom view. Instead of looking at the number of customers in each hour, we can also focus on the time between two consecutive customers. For example, if you look at the first customer, second customer, the time between the arrival of these two customers is actually 62 minutes. And the time between the second and third customer is 40 minutes. The time between the third and fourth customer is 123 minutes. So you can look at the inner arrival time between two customers. So this is called what? Exponential distribution. So basically exponential distribution and a Poisson distribution model the same process, which is Poisson process, but we'll look at the same process from different perspectives. One is look at number of customers in each hour. The other one is looking at the time between two customers.